Okay. Everyone, I want to thank the organizer for having me today with this talk. Today I want to talk about higher derivative corrections to string inflation, about a recent paper with Michele, Pellegrino, Fernando, and Pramod. I'll focus in type 2B string theory with LVS potentials. We know that f to the 4 corrections are not captured by second derivative ansatz of the Kähler and superpotential. In fact, it comes directly from higher derivative terms in the 10-dimensional theory after dimensional regularization. This potential in LVS can be written as in equation 1, as the first term is an alpha prime cube term, non-perturbative terms, where the first depends only on the volume, then the second on the volume and the fourth cycle, while the second only on the 2 cycles, and f to the 4 corrections that depends again on the 2 cycles. So in principle, it's not possible to invert the dependence between the 2 cycles and the 4 cycles. And so we have that the dependence on the topology is very crucial, is really, really crucial. So in general, these f to the 4 corrections are important because they could lift flag directions that are left from the LVS leading order, and they could modify slow roll as an inflation by steepening the potential and so changing the phenomenological data as the spectral index. This f to the 4 corrections takes the form in equation 2. So we have a parameter gamma that expressed in equation 4 encompasses string coupling terms and lambda, that is a combinatorial factor that was calculated in a 1 modulus case to be around 10 to the 4, 10 to the minus 3. And is suppressed by the volume powers as v to the 4. And there is a combination between the periods pi that are basically topological data from the second shared class wedge, the divisors, the dual of the divisors, times the 2 cycles. So we want to understand these pi's, and we performed a scan between odd number from H11 from 1 to 5. And we want to classify these divisors for different pi's. We have that pi is given as in equation 5 as a combination of the early characteristic chi and the holomorphic characteristic chi h, with their odd number description in equation 6 and 7. So we have that the pi is equal to 0 when chi is exactly 6 times chi h. We ask, can we find pi equals to 0? We perform a scan for such divisors that we call dpi. And we identified 3 different classes where this can happen. The first class is a del pezzo free, so dp3. In this case, we have that h20 and is 0. H10 is also 0. So there is only this possible Hodge diamond. Then we identify Wilson's divisors, where we have Wilson lines. So h10 is bigger than 0. And the third case is non-rigid, where instead we have h20 bigger than 0, but let me point out that no known examples to our knowledge have been found about this geometry, this topology. So the scan results are that only divisors that we found are dp3 with h11 bigger than 4, and Wilson divisors with h11 equals to 2. It will be important for poly-instantons, for example. No T4 divisors were found that are suitable for LVS and pi equals to 0. No Calabi-Yau that are suitable with h11 equals to 1 and 2. We found no shrinkable dp3 with h11 in the range from 3 to 5. And then the only dp3 that can sustain LVS is, so with also the diagonal del pezzo is found only for h11 bigger than or equal than 4. While the cases with h11 smaller than 4, smaller or equal than 4 with LVS, we found only 1 case with Wilson divisor, and only 1 case with diagonal del pezzo, and 3 vanishing pi's were found with LVS. So in principle, we cannot have pi equals to 0. So we ask what happens if one of these corrections is present. Is inflation safe? So we will now analyze 3 different models of inflation. So blow up, fibre inflation, and poly-instantons, and check if these corrections are actually dangerous or not. or they might be even helpful. So first, we focus on blow up. We analyze a simple case where H11 is equals to 3. While the inflaton is played by the modulus tau 2. So the correction is expressed here in equation 8 with a really cumbersome equation. And the ideal case to eliminate these corrections would be to have the pi b, so the big modulus correction equals to 0, and pi 2. Since pi 1 it's already stabilized, the tau 1 is already stabilized at the higher is already stabilized, so it will just provide you a shift of the potential. Now, no corrections to the dynamics of the inflation. However, we have difficulties in finding pi b equals to 0. In fact, taking the full potential that is given by LVS, the uplifting part, and F to the 4 corrections, where the uplift is given as a constant d over the volume to the 4 thirds, where we are choosing this parameter d in order to have post-inflation a Minkowski vacuum. While let me point that the volume mode, the volume minima is different during inflation and after inflation, while during inflation is bigger. So it will suppress more these effects. And inflationary dynamics is given in equation 10 as the first line, that is the usual leading term, plus the corrections that are in the second line in blue. Where phi is a linear combination of canonically normalized field, the other 5 are phi. And the coefficients are all powers, have all scaling of the powers of the volume given here in the last line. So this, since we are taking this correction, we can calculate as always the slow roll parameters and then calculate the number of foldings. And we need a number, an exact number of foldings in order to predict observables. How to do it? Let's see how the rating happens in these models. We are assuming the standard model on a D7 stacks, and an important interaction between the volume mode and the X of the standard model is given in equation 13, that is loop enhanced. And we can point out 2 different scenarios where this interaction will play an important role, where we can have a D7 wrapped around the inflaton cycle or not, basically. So let's first analyze the no D7 on the inflaton. The lightest modulus is the volume mode. So the volume mode will decay during inflation, so it will not play any role after the inflation ends. In fact, we will have only a matter-dominated epoch, and that will, after tau 2 decays, so the inflaton decays, we will have reheating. This decay rate is given, decay width is given in equation 14, is volume suppressed as volume to the 4, which leads to an epoch of matter domination given in equation 15, so 5/3 the log of the volume, giving the total number of foldings for inflation in equation 16. So we have 50 minus 5/12 log of V, where we are assuming that the tensor to scalar ratio is around 10 to the minus 10, as in usual blow-up models. So this will give us a problem with the number of foldings. In fact, for standard volume, like 10 to the 4, 10 to the 5, 10 to the 6, in the end, we will have that the number of foldings around 45, 44, 46. So the spectral index could be too red, so too low to match the measured values like Planck. And different result we have in the case where we have a D7 on the inflaton cycle. In fact, we have an enhanced decay of the inflaton. So the lightest modulus is now the inflaton that first dominates after inflation. So we have a first matter-dominated epoch. Then it decays. The volume mode now starts to dominate. So we have a second matter-dominated epoch that, when it decays, will give us reheating. So we have now 2 epochs to check. So first one from the inflaton that give us a number of foldings now that is 1/3 log of V, since now the volume suppression is different. And the volume decay that is given by the loop enhanced interaction that we saw previously with the X's, that is given in the end as 2/3 log of the volume minus the number of foldings of the first matter dominated. So putting all together, we found that the number of e-foldings is now 50 minus 1/6 log of V. So in the end, these two matter-dominated epochs combined last less than the single matter-dominated epoch when we had node D7 on the inflaton. And this scenario so is favorable because we have a bigger number of e-foldings, so we can fit better the spectral index. In fact, with numerical example, first in node D7, we choose these parameters in order to match the primordial density perturbations. We fix pi b and pi 1 equals to 0, and this is a result that we can, without affecting the general result. With pi 2 equals to -1, we have done a check with lambda equals to 0 that will give you, let me go instead with the spectral index, this is what the potential. Lambda equals to 0 will give a spectral index that is not in bound with Planck, while these corrections in the end are helpful. So they can start from a reddish spectral index and put it on the, instead on a better value of the spectral index. We found that a bound, an higher bound on lambda is to be 1 times 10 to the minus 3. And this seems to be in accord with a single modulus case analyzing in literature that found a value for lambda around this value, and we expect this to be the case also for multiple moduli. As I showed before, this pi 2 plays an important role. Pi 2 bigger than 0 could give dangerous corrections. In fact, since we are starting from a spectral index that is already below the value of Planck, giving a positive correction will further put your spectral index away from the value. So negative pi are favorable in this case. Different result we have when an n stack of D7 is on the inflaton cycle. Again, we have this choice of parameter, and we can perform the bound on lambda for different values of the stack, of the number of stack. They from 2 to 5 we analyzed, and we found that they are 10 to the minus 3, 10 to the minus 2. In this case, the lambda equals to 0, so no correction at all, is already in bound with Planck. Sorry, I went to do it. It's already in bound with Planck. So even also pi 2, this is a typo, sorry, pi 2 bigger than 0 is viable because if it is low, it can still remain in bound with the spectral index. Let me say that I will come back to this later. We have considered that loop corrections to blow up potential are suppressed because we chose string coupling low, and this could be something to check later. I will come back in the conclusion with this. Let me now first talk about fiber inflation. We have a different geometry from the blow up. We need, in fact, a K3 fiber over a P1 base. And we have here a volume that is schematically given as alpha times the square root of tau 2, tau 3 minus the LVS modulus. And we identify the inflaton as a flat direction along the tau 2, tau 3 plane. First of all, we have that the inflaton potential in this case is generated by loop corrections that instead we were negliging, we are ignoring in the blow-up case, given in equation 22 that scales as the volume to the minus 10 thirds. These parameters A, B, and C are order 1 parameters that are flux-dependent parameters. And in the end, they will give the inflaton potential in equation 23 that is that has these exponentials that are driving the inflation. Sorry. And we can distinguish about 2 different cases for fiber inflation where we have a single K3 fiber or multiple. The first one is where we have a single K3 fiber. The volume expression is given in equation 24. So we have 3 moduli, so H11 equals to 3. And we are parameterizing the inflaton with the tau 2, sorry. And the correction, the f to the 4 correction is given in equation 25. As we can see, again, pi 1 does not play any role because it's just a constant shift of the potential, since tau 1 is already stabilized. And again, the ideal case would be that of having both pi3 and pi2 equals to 0, so that no correction at all is in place. Or a possibility is to have pi2 equals to 0 from T4 fiber Calabi-Yau. And however, examples in the CC database of this T4 geometries, T4, without, however, any diagonal del pezzo to realize the LVS were found. So no diagonal del pezzo with T4 were found in our scan. Different thing is instead for the multiple K3 fiber. In fact, here we are analyzing a case where H11 is equals to 4, so we have an extra modulus, so another flat direction at the LVS level. And the correction will now feature another modulus. And the possible stabilization will give us back the same scaling as we obtained in the first in the single K3 fiber. However, examples with full T4 fiber for all these moduli, with also a diagonal del pezzo to realize the LVS, are yet to be constructed. So this is still an open question to the literature. Let us now go again for the reheating. In fact, now to extract phenomenological data, we have that inflaton potential in equation 28. The first line is the one that already presented in the previous slides, plus these corrections in the F2-4 correction, with the coefficients R2 and R3 that are volume suppressed, one of the volume. They depend on the combination of lambda pi, that are much, much smaller than 1. However, R3 is a dangerous term because it has a positive exponent. So it could ruin completely the inflaton potential, so the steepness of the potential can be destroyed. While the other term is a negative potential, so it's not dangerous. Let's focus again with the standard model on a D7, with the volume Higgs coupling given in equation 29, now expressed through the gravitational mass squared times C0 plus the loop coefficient times the log of this case as the volume times the Higgs squared. This means that the ratio, the decay ratio between the inflaton to the Higgs over the inflaton to radiation sub gammas is given by C loop times volume squared, that is much bigger than 1. So this means that the inflaton mostly decays into Higgs. This means that the number of e-foldings is given now in equation 31 by equals to 53 plus 1/6, and this combination of the volume and the gravitational mass time over the inflaton mass. This will play an important role here in the numerical example. In fact, now we set R equals to 4.8 times 10 to the minus 6, with pi2 equals to 24, since we are forced to take a K3 vibration, so pi2 could not be equals to 0, it's forced to be 24. And pi3, sorry, equals to 1. We have that the potential here is represented. As you can see, we scan for lambda equals to 0 to the uncorrected one. In correct case, to lambda equals to 10 to the minus 4, 10 to the minus 3. We can see that here the effect is more noticeable than the case where we had the blow-up models. In fact, the steepness of this potential, this plateau, gets destroyed. Basically, we became different. The spectral index here shows a much wider range of values in respect to the blow-up case. And again, with the best fit given here by the spectral index, we have that the upper bound of lambda is 10 to the minus 4. 6 times 10 to the minus 4. That is different from the previous bound that was 10 to the minus 3. So this is even a lower bound, so it allows more values of lambda. And again, the single modulus case that was around 10 to the minus 3 is still suitable with this bound that we found. So it still gives us a correction that is not dangerous. Now, let me briefly talk about the poly-instanton case. First of all, we must have a Wilson divisor that will give us the volume in equation 32. So we have the usual big cycle, the small cycle with 2 LVS, minus this other term that involves the tau Wilson, we call that. And this will give us the f to the 4 correction in equation 33. So these v to the 4, in this case, are again gamma over the volume to the 4. We have a term that is given by the big modulus, a small term that is stabilized at LVS, so it will not play any role, and pi w. So we must ask if these corrections are dangerous or not. We found that in the scan, we found Wilson divisors which allow for pi equals 0. I remember to you that it was the case where h11 was equals to 2. So these are the only case where the Wilson divisor are equals to 0. So we can topologically tame these corrections. And in regard to the big cycle induced terms, they scale as the volume to the minus 14 thirds that are much more suppressed than the scale of LPS. So they will not play any role. In the end, we can ignore them. So we can say by this analysis that poly-instantons predictions are preserved by f to the 4 correction. So let me now talk about the results. We found that periods that are equals to 0 requires that the divisor as that the earlier characteristic chi is equals to 6 times the holographic characteristics. Our scan found that only DP3 and Wilson divisors are suitable to obtain these. However, I recall that we only analyze from 1 to 5, H11 from 1 to 5, so possible other analyses are to be done in the future. In general, from our analysis, both blow-up inflation, fiber inflation, and even more from poly-instanton inflation, these f to the 4 corrections do not spoil inflation if we are with parameters inbound, so with lambda that is inbound. Or even this correction in certain models could help achieve the right phenomenological data, so the right spectral index, for example, if the uncorrected case is out of bound. So these f to the 4 corrections are also welcome in a certain case. Possible outlooks for the future, as I mentioned before, these loop corrections that we assume to be absent in the blow-up case, because we said that they were not entering the inflaton potential, and we were saying that they were absent. However, one should be more careful about this statement, because if one assumes a small coupling from string to eliminate these loop corrections, this implies that the volume is very big, since the volume has an exponential dependence on the string coupling. So since we also use this volume, the value of the volume to match the density perturbation to the actual value, the smallness of G string could give us a volume that is too big to match these predictions, and so this fit could not be anymore valid. So in general, this concludes my presentation. F to the 4 corrections are dangerous. The answer is no, almost no, because sometimes they could give you some problems, but they are tamed if you take the parameters in the bound that we have found, and possible future development will give us more insight on the full theory, on the full models, with also including all possible corrections to these inflationary models. Thank you all.
Thank you, Matteo. Are there questions? Okay, maybe while we wait, I can ask something. So can you remind me how, like in general, is computed the lambda this parameter lambda, like from top down, I mean?
Okay, yeah, it's computed by, I don't remember, it was an integral over some geometry piece. Now I don't remember exactly. It was computed only if I'm not mistaken, in an n=2 case with only a single modulus. But
okay, so these values are specific for this single mod.
I don't remember right now the actual computation. Yeah.
Okay, that's fine. Thanks. We have a question by Michael.
Oh yeah, I just had a quick question. Your plot of the inflationary potential, if you could go back a couple of slides.
Yes, which potential?
That was nice. It was like a slow roll type potential. It was a plot.
The fibre or
no, maybe that was there was one.
This one?
It was fairly near the end, I believe.
Okay.
Yeah, so that might be one there, but there was another one further on, I think.
Okay. Maybe
anyway.
This one, maybe 28.
Yeah. Do you have a plot of it? There was a plot.
I think the plot for fiber inflation.
Yeah, this is it.
Okay.
So this is fiber inflation, is that what it is?
Yes.
Okay, so this looks very familiar type of a plot that they have for slow roll inflation, except it seems to go up towards the right. I forget, there's a particular inflationary model which is very popular. I forget the name of it offhand, but anyway, it goes flat to the right, dips down to 0, and then goes exponentially to the left. So that's basically the general behavior you have, except it goes up to the right. And then the question I had was, and to get those inflationary potentials, they usually fine-tune the bottom so that the vacuum energy is at 0.
Yeah,
is that what you did, or did you get naturally that it came out to be 0 at the bottom? Because it seems like that's all you just kind of put in.
Okay, yeah, to achieve equals to 0 the background. So in Minkowski, we use this, I think I've written in the blow-up case, the uplifting term given in by here. So this is mostly put by hand. It can be motivated by all kind of construction to give you this kind of power law. But in general, we assumed it was this. We tuned we chose the parameter D in order to have Minkowski, and then realize inflation on top of that before. So it was, yes, was done basically by putting this uplift term, yes.
Okay, so there is some subtlety there with how you do the uplifting, because that's always very difficult, right, to get the uplifting.
Yeah, there is another mechanism in literature that could give you this scaling for the potential. Yes.
Right. Naturally, if you didn't do that, it would be negative.
Yeah.
But so that you can show. All right, that was just a general question I had. But the fact that this particular plot that you're showing right now goes flat to the right, whereas the other one goes up. Is there any implications for that? Are there any? Does that have any effect on any observables, or it doesn't really matter?
Well, yeah, the steepness change, the slow roll, the exit, basically the point of exit of inflation. So changing the steepness, that means we are enhancing this R⁵ correction. Sorry, not R⁵, R3 correction will increase the steepness, and so the inflaton will change its exit point. That will reflect, if you look at this plot instead, to a higher value of the spectral index. So we are pushing the spectral index up by increasing the exit value of the inflaton. So this steepness, if you have the plateau, is different. Instead, if you have these corrections, will give you a different value of the spectral index. Yes.
Oh, excellent. Okay, thanks very much.
Can I add something? Nicole, can I add something?
Of course, yeah.
Yeah, so I had a paper in the past with Alexander Westphal and Francisco Pedro, where we actually use this steepening on the right-hand side, because what happens is that this will give you an epoch of, an epoch of fast roll before inflation. So you have a transition from fast roll to slow roll just before the beginning of inflation. And then you can check that it's very hard to get a lot of refoldings of inflation because of these corrections, then you get this steepening. So which means that in terms of phenomenology and observations, you tend to get just enough inflation and this fast to slow roll transition before inflation. And this can be seen as a power loss in the CMB at large angular scales. Because this gives you a loss of power. You can check the amplitude.
That's interesting. Is that something they can measure in the future, or is that something that you?
Well, at a certain point, there was a the main problem there is the fact that it's hard to have a lot of data because of cosmic variance when you are at large angular scales. But in principle, they could improve on that, yes. And they see a kind of loss there, even if the statistical significance is not very high.
Michele, sorry, just to understand, but the power loss was related to the steepening on the right, right?
Yeah.
Okay.
And then at a certain point, when you go a lot towards the right, you shouldn't trust that potential anymore.
Yeah.
Because you are in a regime where the effective theory is not under control.
I think we have a question by Arthur.
Yes. So my question is, I think, in particular to Michele, but maybe also Matteo can answer. In these models or in this
Well, Matteo should answer, I guess. He's the speaker.
Well, but you refer to your own previous paper without Matteo, so I don't know who can answer. But has there been an analysis done in such potentials, what the initial conditions actually are? I mean, if you're in the landscape, and we believe in the landscape for the purpose of this analysis, right? Then there's a previous tunneling process where from some different vacuum, de Sitter, or maybe directly from Hartle-Hawking, you get to this potential. And then it is not obvious to me whether you are likely to end up on the plateau or, as you said, likely to end up on the right steep side. What can one make a quantitative statement about this? Or how do you make your assumptions about where you start?
Well, our assumption...
okay.
Yeah, Michele, you want to...
No, please go.
No, yeah, the exact point where we were choosing our initial inflaton value was to match the number of refoldings that was required by the reheating. So we were putting the inflaton in the right place to achieve the right number of refoldings.
I understand that, but I guess the question is whether you initially start in a regime such that this point, which you choose by observations, is already in a slow roll regime, or as Michele suggested, you may consider that you are so high up that you actually fast roll to that point.
All the cases were already in the slow roll regime, yes.
But yeah, so this is an assumption, and my question is more, whether anybody has tried to go beyond this assumption. Maybe in Michele's paper.
No, okay. So let me say there are two issues. One thing is that an honest answer to your question is that I don't know. Okay, because we haven't analyzed this issue of initial conditions in terms of maybe tunneling from a higher vacuum, and that would be very interesting. I agree with you. And the second issue, which we instead analyzed, was about the length of the inflationary plateau. Okay, so you can check, regardless of initial conditions, how many foldings you get in general. So do you get 50, 60, or there are examples where you get 120 or whatever. And you find that because of these corrections, it's very hard to get more than 60 foldings.
Because of which corrections? Of the new corrections, of the presently found higher F-term corrections, or which corrections?
No. Even without the higher terms. For example, you look at this plot. this plot has also lambda equal to 0, and there is this steepening which is still there from loops.
I understand. And that's steepening.
And basically, because what happens here is that you have the base and the fiber, and the volume is kept constant during inflation. And this, I know you know this, but maybe for other people. And during inflation, what happens is that the fiber gets smaller and the base gets larger. So at a certain point, there are some cycles which become small and some corrections blow up. And so if you have only 60 foldings, then it's different than having 120. So you can have this pre-inflationary epoch with a different equation of state parameter for the background. Of course, you need to end up there with the initial conditions, because you could have only 60 foldings, but the initial conditions are such that you start from 30 foldings, and then the whole thing doesn't work. I agree. But of course, if you have 120 foldings, it might be that there is no power loss at large angular scales.
Thank you. That was exactly it. Thank you.
Yeah.
But sorry, maybe I didn't get it correctly. So you said that you couldn't have a plateau which is too large, right? But so in that case, so maybe I'm just rephrasing what you just said, but if you start from the fast roll part, then you would never, I mean, you would arrive on the slow roll part with like kind of initial speed, right?
Yeah, but then it goes to 0 very quickly.
Okay, that was my concern. If the plateau is not too far, then you...
No, that works.
That's not a problem.
That works. Yeah.
Okay.
So thank you for the discussion. I think we can stop here the recording, and but you can go on with the questions and discussions if you want to.